Good morning, everyone. Thanks for joining us today. Got an exciting lineup of presenters. We're just at 10:02 now, and I think a lot of attendees are here, so we're going to jump straight into it. And I'll introduce our first presenter. Our first presenter today is Allan Hosking. Allan's a trained surveyor from Otago, dating back 1989. He's been involved with various forms of 3D laser scanning for over 20 years worldwide in Asia, United Kingdom, and for the last 10 years he's been back in New Zealand. So exciting to have him with us today. He's currently working with Survey Solutions based in Tauranga. I'm sure some of his clients and customers will be familiar with him, hopefully a few here today. He's specializing in supply of mobile mapping technology with a GeoSlam system, which comes from England. The GeoSlam system, as the name suggests, is a SLAM-based system and was jointly developed initially by CSIRO in Australia for research over the last 12 years. So we'll jump straight into Allan's presentation here, looking at handheld laser mapping.
Thank you, Sam. I hope you can all hear me okay. So thanks for inviting me along today, Sam, and the rest of you guys. It's a pleasure to be here. I'll try and stick to the time slot of 15 minutes. Just to give you a bit of my background, Kiwi born in Havelock North, went to Otago Uni, like Sam mentioned, got registered as a surveyor in '92, and then in those days there wasn't much work on, so most of us went overseas. So I spent the beginning of my career in the Middle East, and then after that moved on to Singapore, Southeast Asia, and then after that the UK. And then 10 years ago, moved back to New Zealand to live here again 10 years ago. During that time, I was fortunate to get extensively involved with 3D scanning in various forms, during that overseas time. So it's been a challenging, fun time doing 3D scanning, and I hope you enjoy what I have to say today. Survey Solutions as a company, we're a small company, but we're specialising in 3D scanners. So we supply a range of scanners that are handheld and mobile. Some of them are from a company in Luxembourg called Artec, and the other ones are from GeoSlam in the UK. We've sold loads of them all over New Zealand, the movie companies and oil and gas and engineering and all sorts of weird and wonderful applications. GeoSlam as a company, they've been around now for several years. They're based over in England, but they've got a distributor network worldwide, and of course that's what we are part of, the distributor network. They have some regional offices as well, and the nearest one is over in Brisbane in Australia. What they supply is a range of handheld scanners, but actually in the last couple of years they've really diversified into systems that are very versatile. So the one system can be modular and you can expand it to do what you need. For example, not just handheld, but you could mount it on a UAV, you could mount it on a car, or you could put it in a backpack. And there's a whole bunch of camera options that you can get for imagery, and it could be a cheap 360 camera or a video camera, or it could be a high-end NC-Tech camera. So the GeoSlam systems, they're based on SLAM, and I don't know how many of you are familiar with SLAM, but SLAM is basically you have a Lidar sensor and you have an IMU, an inertial motion unit. And those two devices are in the one package, and you're traveling around the site measuring. So SLAM is identifying objects and features in the scene, and it's doing the registration of the scan while you're walking around using the objects that it sees. And that could be trees, buildings, cars, any sort of structures that happen to be around you. And then when you come back to the office, you have your 3D point cloud. The important thing is it doesn't need GPS, and it's mobile. So you just move around through the work area and it just measures everything within line of sight. So it's very fast because of the portability and the mobility. People often question, well, why should we use a mobile scanner? Why can't we just do it with a tripod scanner? Well, a lot of sites nowadays and a lot of projects, the timeframes are very short and access to the sites can be quite difficult. So having a device like a handheld mobile scanner can really reduce significantly your survey time on site. And often you can do jobs in minutes or half an hour that might take all day using a conventional tripod scanner or some other form of survey tool. There's also less disruption when you're on site. So if you're on a construction site, the contractors can all keep working. They can just keep carrying on with whatever jobs they're assigned, and you can, as a mobile scanner, just walk and move, travel through that work area, measuring without interfering with anyone on site. And that goes the same for, you know, public areas where you're moving through, say, an inner city street and there's the public all around. You're not interfering with them at all. You know, it's eye safe, it's class 1 laser, so it's really just, there's no disruption to the work area when you're scanning. And of course, this opens up a lot of new business opportunities. You know, having a device like that, it opens up a whole bunch of new opportunities that you may not be aware of or weren't aware of until you start applying the technology. You can certainly take on projects that previously just weren't considered feasible. And one interesting thing is when people start working with mobile LiDAR data from a handheld scanner, they notice very quickly there's less occlusions in the data. And the reason being is because you're mobile, you get up close and personal and it's quick to move around the areas of interest that you're trying to scan. And it works very well in very congested sites. So the more congested the site, the faster the survey is. That's the direct opposite of if you're trying to do it with a tripod scanner. Geo-referencing obviously is an important part of the survey. So we have 3 different methods of geo-referencing that data to your local control and so on. There's the traditional method of using checkerboards. So obviously during the scan it picks up those checkerboards as using the grayscale intensity and geo-reference the data that way. There's the option to attach a reference plate to the handle of the base of the handheld scanner. And so you can notice on that diagram there's a little cross. It's for centering over the control point. So you walk around the site scanning, and as you come past a control point that's been put in by total station or GPS, you sit the laser on top of the control point for only 10 seconds, centering it with that cross. Leave it stationary for 10 seconds and the system will automatically log and record the control point. And then for other sites, you might find it more convenient to possibly use GPS. So of course you can mount the GPS above the LiDAR sensor and geo-reference the data that way. So you've got, those are the main 3 geo-referencing techniques that people would use using a mobile scanner. So the general workflow is obviously you go to site, do your 3D scanning on a UAV, handheld, put it on a vehicle, you know, whichever's appropriate for that site. Collect the data. Back in the office, depending on the sensor, some of the sensors we can process the data real time in the field, others we've got to drop it into some software back in the office to run the SLAM algorithm, so it depends very much on which make and model you use. And that SLAM, which identifies the shapes and features as you walk around, generates that 3D point cloud. And of course that point cloud is then no different from any other 3D point cloud. It can be taken off into third-party CAD packages for, you know, drawings and 3D modeling and so on. Like most softwares nowadays, they have a free viewer. So for sharing the 3D data for stakeholders in the project that don't have licenses of software, you can provide them with a free viewer for reviewing the point clouds and the trajectories and the paths that you've walked along. And of course the viewer has some tools in it for spatially sampling the data and re-exporting the data in various alternative formats. Another popular question would be accuracy. So accuracy is pretty much like a total station. You know, the instrument might have a specific statement for accuracy, but it depends very much on how the survey was carried out. Is the environment SLAM friendly? I.e., is there a lot of features and objects for the SLAM to see and identify to position itself from? How long did the survey take? The shorter the survey is taken out, the higher the accuracy. Just like traversing with a total station. You do a long traverse with a lot of legs, you're going to get a lot of error, right? So it's a similar concept for the handheld mobile scanners. The distance you're measuring at, obviously if you're measuring points, surfaces that are 100 metres away, those points will be measured less accurately than if you're measuring surfaces that are only 10 metres away. So, you know, distance affects your accuracy. And of course the design of your survey is important. Again, just like a traverse with a total station. If you have poor traverse layout and design, poor network design, you get a poor result, right? It's the same with a mobile scanner, similar concept. We need to have closed loops, just like a closed traverse, and design them well to improve and get the best results. And of course, the most important part, which surveyors would be the most adept at dealing with, would be putting in control points as for quality control on the data that's collected. And also, if you've got good control on site, you can adjust the scan data to best fit the control points that are available. So having control points on site is a way of improving the accuracy and having better quality control. So to summarise all that, typically your accuracies, you're looking at relative accuracies, and when I say relative, that's over a small area, you know, 10, 20 metre radius type of area. You're looking at relative accuracies between objects measured of an XYZ of 10 to 30 millimetres, taking into account the above factors. And of course, absolute accuracy, sticking it on a local coordinate system projection, using your control, you can get between 30 and 50 millimetres in absolute over the data set. So it should give you a pretty good idea of accuracies there. So deliverables, your fundamental basic deliverable out of any LiDAR system is going to be your point cloud. So again, depending on which make and model you're using, obviously grayscale intensity, your black and white, you know, for picking up lines on road and paintwork and so on, or your RGB color if you've been using a camera during acquisition. And if you've used a video camera as well attached to the device, you know, you might have still images or video. So just to give you a brief idea of how long it takes to measure things, here's a sample data set collected around the Tauranga Hospital, just externals only in Tauranga. Although you could go indoors and outdoors at the same time doing acquisition. In this particular case, it's purely externals. It was collected with the GeoSLAM Discovery system. On top of that has a 360-degree camera, very high res, 60 megapixels. It's the iStar Pulsar NCTEC camera. So that acquisition there, that was collected in a total on-site time of 15 minutes. So that's pretty quick, and you end up in this particular case with a very rich colorized point cloud. You can see the blue line there is the track that I've walked along, and the blue line is actually a series of dots that are the actual 360 images that have been collected, and they're recorded every second as you're walking around. So if you look at that screen there on the top, that's the colorized 3D point cloud that was collected. And at the bottom there, of course, is one of the many 360 high-res images that have been recorded on a 1 second basis. So that route was approximately 400 metres. If you look up there, it was quite a in and out complex route. So 15 minutes to cover that area. So incredibly fast. So the speed of acquisition is really a big benefit of using a mobile scanner like this. Obviously, the data, when we take it out of the softwares for processing, they go out and export to your standard CAD packages, whether they're Autodesk or Bentley products or Esri or some other scanning package. So in New Zealand, it's still very much a niche market. We wouldn't say it's extensively used all over the country, but we have several customers that are using them. At the moment, the main users that have brought them and are using them as of today in New Zealand are in the oil and gas over in New Plymouth, doing onshore, offshore mapping of platforms and FPSO and onshore processing facilities, ports and airports around the areas, BIM management on buildings. Owners of large property portfolios obviously benefit hugely from a tool like this that can in minutes go and map very complex spaces and get it into their BIM systems. Industrial warehouses, digital twins for automation and tracking and planning of robot movements through industrial warehouses is another common use of it that we're doing, and other obscure applications like forestry. So that's it from me. I hope I've kept to the 15 minutes, and I'll pass it back over to you, Sam.
Thank you, Alan. That was very interesting. It seems to me like a little bit black box, black magic, but I've seen the results, so it is believable, even if it seems a bit unbelievable. I just have to comment here, if anybody has any questions coming up, we're going to sort of do questions and answers collected at the end, so just shoot some questions into the Slido. I think a lot of us have been introduced to that before, so anytime you see a question, think of a question, pop it in there, and we'll try to make sure we run through it at the end. So we'll lead straight through to our next presenter, which is Rodney Pilbrow. Rodney's graduated from Auckland University with a Bachelor Engineering in Mining. He spent 5 years in South Africa working in coal mines before returning to New Zealand, and now he's working with Pilbrow Surveying Limited since 1995. So we welcome Rodney this morning. He's a director of this specialist company, and people attending today may have seen his face before. He's presented for Survey and Spatial several times before with some of his cool technology. He's working with quarries and bulk earthworks and landfill operations and land development, and applying his technology in those environments. He's been using unmanned aircraft since 2011, so he definitely is a market leader in terms of uptake there. There's no doubt about that. And he's been using Lidar on his UAV since 2017, so also a market leader with uptake there. So we'll welcome Rodney this morning, and please jump straight in.
Good morning. So as Sam has said, my presentation today is going to be on my experiences using Lidar on my UAV systems. Sam has already briefly run over my history. As he said, since 2017, I have used the Lidar on our UAV. Today, I will firstly discuss why I moved into Lidar on the UAV. I will talk about the specification of our systems and how it has developed since I first acquired it. Then briefly explain the operation and touch on some difficulties. I will show some examples and answer questions. Most UAV systems use a camera as the sensor to capture images and photogrammetry to extract surface data. For a rock face in a quarry or a bare clay surface on a construction site, this is ideal. However, there are many situations where it is difficult or impossible. Anything which is moving, such as water or leaves blowing in the wind, will not match correctly. Features which are very similar are also difficult to process. For instance, tiles on roofs of buildings, chip-sealed roads, or large stands of pine trees. The reason is that photogrammetry requires at least 2 images of a point to be able to extract the position of that point. If the object moves between the 2 images, or if the gap down to the ground through vegetation is not large enough for 2 images to see the same point, then there will be no data. This is where Lidar has the advantage. Only a single return is required to get a position. It only needs a very small gap in a tree canopy for the laser pulse to get down and back. Most of our surveys are done to capture ground data, and that is what is needed for volume calculations or design work. The photogrammetry from our unmanned aerial systems provides great data for the working areas of our quarry clients. However, nearly all quarries in New Zealand and many construction sites are surrounded by vegetation. So practically right from the start, I was asked, can I survey those areas with the drone as well? And I had to tell them no. For those areas, we had to get in there with the total stations or get them to clear away the vegetation to allow us to do the survey. It was for this reason that in 2015, I began a 2-year investigation and development process, which culminated in our purchasing a Snoopy Lidar system from Lidar USA. This consists of a STIM 300 inertial measurement unit from Novatel, and our first system had a Velodyne VLP-16 puck. The initial results were okay, but they were not as good as I'd been hoping for. As my trials went on, the data seemed to be getting worse. Eventually, I found that the lasers in the puck were failing. It was sent back and replaced under warranty. While the system was in the US, I decided to upgrade the laser to the Velodyne HDL32. The lasers in this unit are rated for a 2 centimetre accuracy with an 80 to 100 metre range. The updated system worked well, and we were able to get some impressive results in very dense vegetation. After using the system with the HDL32 laser for a couple of years, I was finding some shortcomings. For our quarry sites, the main problem is maintaining line of sight and clearance with the unmanned aircraft while carrying out a LiDAR survey. The maximum effective range of 80 metres for the HDL32 means that for sites with large elevation differences, I was flying below the height of some of the trees in the upper slopes. This picture shows where images for the photogrammetry flight for this site were captured, and these were around 120 metres above the ground. But to be sure of getting ground strike with the LiDAR, I had to fly 40 metres lower. And as you can see, this is starting to get very close to the treetops in places. This is not pleasant to do and was my major cause of stress at that time. I also found the data from the Velodyne lasers to be very noisy, and that restricted the type of work I was able to do with the LiDAR. To overcome the range restriction, I upgraded the LiDAR in the Snoopy unit to a Regal Minivux 1 UAV. This new laser has an effective range of 150 metres with an accuracy of 15 millimetres. This new setup has made it possible for me to survey some exceedingly difficult sites that I could not do before, and the data is coming back much cleaner than from the Velodyne lasers. Any LiDAR unit on a drone will consist of the following things: a GPS antenna, an inertial measurement unit, a laser, and a computer to record all the information. The GPS records where the machine is as it flies along, and the IMU records how the machine is tilting while the laser measures to the ground. Then appropriate software is used to fit all this data together. When mapping, we create a flight plan which allows for parallel runs across the site. For very dense vegetation, a cross run might be planned as well. To achieve good accuracies, the data is post-processed, so I set up our GPS over a known point to log during the flight. While flying, the system is recording GPS signals, IMU data, and laser returns. After the flight, the IMU and GPS data is processed to create a trajectory file. This specifies where the laser was and how it was oriented during the flight. Where possible, ground control points are placed around the site to enable the software to check for and correct any misalignment during the flight. The trajectory is then matched with the laser data to create a geo-referenced point cloud. While the operating principle of this LiDAR system is simple, there were a few areas which caused me problems. In New Zealand, we have a bewildering number of datums, projections, and heights. And as the system was made in the US, they did not have all these immediately available. I had to prepare appropriate configuration files to correctly work for our sites. Most of this information was available either from the LINS website or Global Survey. Unfortunately, not all of it was in the necessary format, so I had to spend a lot of time sorting that out. The worst were the geoid and local mean sea level datums, as the data had to be in a very specific arrangement to work with the software. I have also had issues with the bore sight and lever arm settings. These refer to the spatial relationship between the laser, IMU, and GPS antenna for the particular setup of your system. They only need to be measured once for each setup and are then used as the default for further work. Initially with the HDL32, when checking overlapping runs of data, I was seeing height differences. After much toing and froing with the manufacturer, I found that I'd been given the wrong bore sight settings for that laser. From the start, I found the data from the Velodyne lasers to be very noisy. By this, I mean that the point cloud produced on a flat, hard surface would be around 50 millimeters thick. For areas under vegetation, this was not such a problem, as any data was better than nothing. However, it was difficult to extract a clean surface from hard areas, so I continued to use the photogrammetry for those areas. The Regal laser is much better, with the point cloud on a similar surface only being around 20 millimeters thick. This means it can be used to extract data for roading, as it is around the same accuracy as GPS. I will now show you some examples of the results I am able to achieve using the Snoopy LiDAR system. Firstly, when we had the HDL32 laser, this image shows a portion of a forest park near New Plymouth. The bush here is very dense, as you can see. The survey was to provide a surface for designing a new footbridge. To maintain an effective range to the ground, I had to find a place where I could keep sight of the drone while flying low enough to get ground returns. This video shows the point cloud captured for a portion of that site and shows the ground surface which has been pulled from that point cloud. As you can see, the vegetation shows clearly in the point cloud, and features which are obscured by the vegetation, such as this track and drain, show up nicely in the resulting surface model. This next video shows a point cloud captured at a quarry where overburden removal was planned to be extended into the area under the trees. The tree removal was to take place at the same time as the stripping, so to get a surface for calculating the volume of overburden, we used the LiDAR to obtain ground points for modelling before they started any works. This video shows a point cloud captured to obtain the clearance between high tension power cables and the trees beneath them. This video is a portion of river which had vegetation on the banks. A surface was needed to design a new bridge across the river. To get this surveyed traditionally would have required abseiling down to try and get access. Flying the Lidar completely avoided the need for this. Now a couple of examples with the Regal laser. This site is near Irua, near National Park. It is exceedingly hilly and covered in dense native bush. Due to the limited places to launch from, it is only due to the increased range of the Regal laser that I could now safely fly this area. This video shows a portion of the point cloud captured and the underlying ground which was extracted from it. This survey was for planning access to a new house site. You can see here how steeply the terrain sloped away from the track along the top of the ridge. The cleaner data from the Regal lasers was clearly seen in a recent survey of an area in South Auckland. The 4-hectare site consisted of a residential area with many trees and houses. My client estimated it would have taken their normal land-based survey teams well in excess of 3 weeks, given the problems with gaining access to the individual properties. We were on site for half a day, place out ground control points and carry out flights for both camera and Lidar. This video shows the point clouds from the photogrammetry and the Lidar, and then the underlying surface which was extracted from them. We went through and checked the surface model for obvious errors, which the automated process had not got correct due to the presence of the houses. My client carried out check surveys within the site, and the levels compared very favourably to the data we provided. In some instances, there was less than 3 millimetres difference. After 3 years of using UAV Lidar as a surveying tool, I have found it an effective means of obtaining a ground surface below tree cover. Using the system with the Velodyne lasers, while it got the job done, however, they were limited to range and the quality of data which they could provide. And this limited the type of sites which I could safely or accurately survey. By upgrading to the Regal, I can now fly higher with less risk of damaging the aircraft and still get good ground returns. And the cleaner data allows it to be used for different types of projects. Where practical, I will fly both photogrammetry and Lidar, as this allows for checking between the two data sets. The combination of colour from the camera images and the point cloud from the lasers makes it easier to comprehend what has been surveyed. Thank you for your attention. If you have any questions, we can answer them at the end of this webinar.
Thank you, Rodney. That was some awesome looking visuals you've got there, and definitely looks like possibly the best tool for some of your tasks that I could imagine. I've done some, in the past, I've done some total station surveying through pine forests and through native forests, and the speed and efficiency and level of detail that you're getting there without breaking a sweat is just phenomenal. We'll invite questions to jump on to the Slido, and we'll be looking at them later on at the end of the session. I see a question there. It's just a question related to this the webinar, but no, we're all up and running. We're running live. Question was wondering if we had a glitch, but must have been the user's end. We'll jump straight into our next presenter and to give him some good time so that we can also have a bit of a discussion at the end. So our next presenter is Lennon Bedford. Lennon, he's a technical specialist with Global Survey. He's based in Christchurch. He's graduated from Otago Uni in 2003, and he's began his career with a well-known company down in Christchurch, Canopy area, and later in Nelson. He's completed licensing, so he's run through most of the career path that is us New Zealanders typically. And he spent an extended OE over in Europe working with Leica Geosystems. So a little bit of flashiness going on there. And he's been working with cutting edge survey tech. So he now, in his current role, he helps Global Survey, helps their customers adopt and maximize the value of latest reality capture, if you want to take it from his words. So he's got involvement in all areas of, I guess, of the technical specialist work. And today he's presenting in the vehicle mounted mobile laser scanning. So let's jump forward to Lennon. Morning, Lennon. Thanks for attending. I'll just hand it straight over to you if you're ready. And
yeah, I'm ready.
And we're looking forward to it.
All right, I'll just get my slides sorted. There we go. So thanks for the introduction, Sam. Very excited to be here. As Sam said, I'm tasked with discussing vehicle-mounted mobile mapping systems. So there's a lot of similarities in the technology as discussed by both Allan and Rodney, but also some important differences. I'm really passionate about this type of technology, and I always jump at the chance to talk to people about it. I'm lucky in my role at Global Survey that I get exposed to all sorts of reality capture technologies, from terrestrial laser scanners through to UAVs. But mobile mapping, I think, is the most exciting because it combines so many different sensor technologies into one. So today I'll discuss the types of data that can be captured with these systems and the applications for that data, look at the hardware, some of the challenges in deploying it, and then some of the quality assurance procedures available to ensure that data is fit for purpose. So when we say vehicle mounted systems, that doesn't mean that it's exclusive to road vehicles. So vehicle mounted mobile mappers can be deployed on the road, but also on off-road vehicles, on rail, like on a high rail in the example below, or even on the water. So you wanted to scan the underside of a bridge or the banks of a river. So really are vehicle independent. What type of data are we collecting? Well, it's very familiar to the types of data that you'll be familiar with from terrestrial or static laser scanners. So point cloud data, essentially, in combination with imagery, usually 360 spherical imagery, which provides a kind of street view type navigation through the data and a kind of visual context and inspection. And then the point cloud is in behind, calibrated to that imagery, and allows very precise 3D measurements and modeling. So why would you use this data? Well, first of all, it's much safer to capture data with a mobile mapper. It takes feet off the ground, especially in dangerous environments such as streets or rail. It's incredibly fast to capture, as both Allan and Rodney have discussed. You're capturing data on the fly, in motion, so you can really capture vast amount of data very quickly. The data captured is more comprehensive than discrete measurements from other technologies. So, and this richness of data really allows really versatile applications downstream for the data. What were some of those applications? The obvious ones for vehicle-mounted systems are big infrastructure, things like roads and highways, rail, or tunnels. And from the point cloud and imagery data, we're able to extract your typical type survey deliverables. whether they be vectorized, line work for lines, edges of seal, wires, that sort of thing, 3D terrain models, of course. And then if you're looking at rail, you can extract rail geometry, clearances to overhanging obstructions or tunnels. Those are survey type deliverables. There's also GIS or asset management type deliverables, where it could be, say, automatic road sign detection and then the comparison of those positions against a database, or pavement analysis. So you could look at the roughness of a surface, a road surface, for example, or cracking detection. So as I've said, the data is so rich and versatile. There's so many applications downstream, all which are supported with rapidly improving software, which can automate a lot of this work. So in terms of hardware, all mobile mapping systems, regardless of the brand, really have a similar array of components which are fused into one. There's the sensors which are capturing the raw data, so the point cloud and imagery. So in this case, we've got a high-end survey grade laser scanner on the back. Could just as well be a mapping grade sensor. It really depends on the application. We'll come to that later. So there's the laser, there's the imagery, which is in this case a 360 degree spherical camera and a combination of side cameras for further detail. So those are capturing the raw data, and then this, in order to position this data in terms of a real world coordinate system, we need positioning sensors, which at the heart of the system is a survey grade high precision GNSS antenna, which is fused with an inertial measurement unit to provide the basis for a very accurate trajectory of the system through space. We're not limited to only point cloud and imagery data, so there's the possibilities to attach external sensors, which could be, say, thermal sensors, ground penetrating radar for the detection of underground services, pollution and noise sensors, or even additional imagery type sensors for pavement analysis or the inspection of tunnel roofs, that sort of thing. So how does it work? So both Allan and Rodney have touched on this. The basis of the data is a very accurate trajectory, and this is, in this case, a combination of the GNSS and the IMU fusion. You then have your scan data and imagery, which is not registered, and then that is synchronized in post-processing and combined to produce the 3D data set. So in terms of the accuracy or quality of the data, it's really important to understand that not all systems are created equally. And just like you would consider, say, the angular accuracy of a total station when you were deploying that for capture or set out, it's really important with mobile mapping to understand the expectations or the project requirements before deciding on the hardware. So in terms of the absolute accuracy of the system, this comes down to the quality of the GNSS receiver. So the noise of the system, but also like its support of multiple constellations, for example, will help in terms of the availability of a position, the accuracy of the position, and also the robustness of that position. The same with the IMUs. So IMUs can be anywhere from the low-grade ones found in the smartphone in your pocket, right through to a military-grade IMU used to guide missiles. So it becomes really important, especially in difficult environments, to have a high-grade IMU to both bridge gaps in GNSS data, but also to calculate the pitch, roll, and heading of the scanner. And then quality of the data in terms of relative accuracy really depends on the grade of the laser attached to the system. So if you look on the right there in the imagery, you can see the difference between a low noise survey grade scanner and a cheaper, lower grade mapping grade sensor. So while the mapping grade sensor will be fine for positioning assets, maybe for a GIS database, you wouldn't rely on the data to, say, automatically extract a curb line with any degree of confidence. So I found this nice plot in a study by the Department of Transportation in the US, available online, and it shows nicely that you can expect accuracies of 10 to 15 millimeters with survey grade mobile mappers, whereas you're starting at a sort of 50 millimeter point with mapping grade systems, and then obviously the expected error increases with range from the scanner. So what are some of the particular challenges faced deploying mobile mapping units? The obvious one is the challenges involved with poor GNSS environments, or in environments where there's no GNSS at all, so in a tunnel, for example. So in the difficult environments, multi-constellation receivers help, just because you see more satellites, you have more availability and a more robust position. For total GNSS outages, you're really relying much more, well, entirely on your IMU to calculate the trajectory. And all IMUs will drift with time when they don't have a position update from a GNSS. And the rate of that drift really depends on the quality of the IMU. You can also use, in those environments, say in a tunnel, you would use ground control surveyed in with an independent means, so a total station, for example, to adjust that trajectory so that within the project tolerances. It's important to consider your proximity to the nearest GNSS base station. So just like we have distant dependent errors on our GNSS rovers, same with the mobile mapping system. So this involves, you could be capturing potentially hundreds of kilometers of road or rail at a time. So this involves careful planning and deployment of base stations. The density of the resulting point cloud is really dependent on the speed of travel. So the laser is a profiler, so it's sending out a slinky of data, a spiral of data out the back of the vehicle as it moves along its trajectory. The faster you drive, the more spread those profile lines are. So the speed, the ideal speed of the vehicle is really determined by the project tolerances. What sort of density data do you need? It also depends on the speed of the laser. So both the speed it's rotating, which determines the spacing of the profiles along the road, but also the measurement rate, which defines the density in a cross-section along the data. And then completeness of data is another challenge. So you can imagine if you're driving through busy city streets and you haven't been able to close down the roads, there's going to be lots of obstructions, moving and parked vehicles, and it can be a challenge to capture data that's shadowed by those objects. So this can be overcome with multiple passes along the same trajectory, or many systems like the Leica Pegasus can be rotated on the platform, so you have angular data to get in behind obstructions. So you've seen the spec sheets show that survey grade 10 to 15 millimeter accuracies are possible. How do you ensure that? How do you verify that? So there's various good practices in terms of quality assurance. The most common is use of ground control. So the same idea that many of you will be familiar with photogrammetry and drones. Ground control points can be acquired as an independent check on the accuracy of the data, and it can also be used to adjust the data to a known coordinate system. They should have ideally be measured with an independent measurement technique with a higher accuracy than the mobile mapper being deployed, which can actually be a challenge because these mobile mappers now are providing RTK accuracy or better, thanks to the IMU, which is smoothing the GNSS data. So normally the collection of ground control will involve some static GNSS or some total station measurements or other. You always work from the whole to the part, good survey principles. So GCPs should be widely distributed throughout the project. And the frequency or density of the GCPs really depends on the project tolerances. The higher the degree of confidence required, the more GCPs you need. And you would also focus your efforts on putting GCPs in areas where the GNSS data is going to be weak, for example. Other methods of quality control, so you could use statistical analysis between mobile Lidar data sets and terrestrial static scans. look at the overlapping data statistically. You could fit cross sections obtained along the road using, say, a total station samples. You could compare those with cross sections extracted from the mobile data. We've talked about multiple passes for guaranteeing completeness of data. This is also creating redundancy in the data set, which can be used for quality assurance. So you typically run 2, 3, 4 passes of a single road. And then you could use statistical analysis of the passes, or you could also look into visual quality control procedures, which you could color the tracks independently and then look at overlapping data, slice and dice it both horizontally and vertically, and look for offsets in the data. And you can see up on these images on the right, it's nicely a blend of two colors. You would see very quickly if if there was disagreement, you'd see a single patch of color, or offsets in your cross sections of the data. So how good is this data? So we've been fortunate to be involved in a series of real-world projects here in New Zealand. This was a trial we ran before we deployed in Nanga around our office. This is the Global Survey Office in Christchurch, captured with the Pegasus 2 Ultimate system. So this is Leica's top-of-the-line survey-grade mobile mapper. Captured the same area with a static laser scanner, in this case the Leica RTC 360. So there's a very low noise scanner. The registered data for this set was within a few millimeters. We georeferenced both data sets, overlaid them in Cyclone 3DR software, and created this heat map showing the differences in the overlapping data. And you can see the vast majority, 70% is within a centimeter, and almost all of it's within a couple of centimeters, the rest being the noise essentially from the vegetation. We worked with the Christchurch City Council on a project with the Pegasus 2. This is you can see the start of the Northern Corridor, a new motorway project, which is going to come into the central city. And they needed survey data of this busy part of downtown Christchurch in a very short space of time. So we deployed the Pegasus 2 together with the collection of 27 control points spread over the site. And you can see here the mean adjustment of the data, a couple of centimeters. We obviously started off a different height datum, so the data was moved 8 centimeters. But the standard deviation of the adjustment all down at the 10 to 15 millimeter level. We also independently verified the quality of the data by deploying surveyors in areas that were safe to capture off the road, measured some curb strings, and compared those with data extracted from the point cloud, and it was all within the project tolerances. Another interesting project was up at the Waterview tunnel in Auckland. So those not familiar with it, this is a 2.5 kilometre underground tunnel. The client required the precise location of a number of assets in the roof relative distance between them along lane lines. So ran the mobile mapper through it, obviously a really challenging environment without any GNSS. So the ground control was established using total station traverse through the tunnel in the middle of the night. And then the trajectory was adjusted to that control in post-processing, and we were able to get down to adjustments at 15 millimeter level with standard deviation less than a centimeter. Really satisfying. So thanks very much. I hope some of my enthusiasm for mobile mapping's rubbed off on you, and be happy to take some questions.
Thanks, Lennon. That is, again, some amazing looking data there. And your last example explored a question that's been burning in my mind, which is when a system based on GNSS with the IMU combined, when you have a complete GNSS outage, what does it really mean to your survey? What impacts does it have? So you've explained that, answered the question preemptively with the total station control running through the tunnel. I can imagine, I would hope that was maybe before the road was live, but I suspect maybe it wasn't. So that completes our 3 presentations this morning, and now we've got a little bit of time for questions and answers. So encourage anyone who has further questions as a result of our 3rd presentation to they're welcome to chuck them on there now. I was going to call dibs on the first question, actually, which has been sitting on my mind since Alan's presentation with the handheld and primarily SLAM-based system, the GeoSLAM, is, Alan, what environments might we consider a weak SLAM environment? So I know that if we're walking around buildings and we've got flat surfaces and we're all surrounded, that has to be a strong SLAM environment, no doubt, which we can imagine from our terrestrial scan experiences. What would we be thinking are the weak SLAM environments where we might need to look at things further?
Yeah, I think anything that's flat and featureless, like a flat plane. So it could be like a rural road, but there's no trees, no power lines, no nothing. It's just dead flat, no features within. As long as you've got several features within 100 meter radius of your position, then you're okay. But there will be obviously times there's projects that don't have that, and so therefore it's not usable on certain projects where there's not enough feature.
That makes sense to me.
The richer the environment, the better, basically.
Yeah, no, that definitely makes sense. Comes to my mind, some of the outback of Australia might not suit the GeoSLAM, but
no, that's right. Yeah, and if you stood in the middle of a rugby field as well, that wouldn't be ideal either because there's nothing there but grass. Yeah,
I see. We'll go to a few of the questions which we've got on the board, and we've got a question near the top by Michael, which is again for you, Alan. It was popped up just after your presentation. So it says, can the GeoSLAM system use the measured control points to adjust the registration or just a global best fit?
Yeah, that's correct. You can do that. So as long as you've got some accurate, reliable control on site, yeah, you can do a best fit. So the SLAM trajectory will get recalculated to best fit those control points.
Okay, so we could think of it as a bit of a dynamic update to the SLAM trajectory.
Yeah, it's like doing a Travis adjustment. You know, you do a Travis with a total station, you get a misclosure, then you redistribute the misclosure. A similar thing with SLAM, but of course the tie down points or those control points, you'll hold those as absolute. So the trajectory between each control point will get adjusted so it ties in exactly with each control point. Yeah,
no, that definitely makes sense. Sounds like a way to maybe make up for those weak SLAM environments is just add a few control points through the job.
No, that's not quite true. You still can't use it in the empty rugby field because the primary positioning of the point cloud is still coming from SLAM. You need the shapes and objects to generate the point cloud. SLAM is the primary positioning, and you're just adjusting, fine-tuning that positioning based on the control.
Okay.
I don't know if I've explained that very clearly, but...
No, that makes sense. You showed a picture with a GPS on the top, so I guess coupling in the GPS solution turns it into a slightly different system, but it's based on the SLAM is what you're describing. Yeah.
Yes, yeah. No matter how you deploy it, you're using SLAM as a identify shapes and objects to position yourself from.
Yeah.
So you must have shapes and objects within 100 meter radius.
Yeah. We've got a question from Wayne, which also popped up just after the first presentation, but I think it applies to all the different systems. But let's ask Alan first, as that's where it popped up. It's likely to be very data storage hungry. What amount of storage is needed to operate? So I guess if we think a typical survey might be 30 minutes, sounds short, but that's a lot of walking around. Do you have a rule of thumb of what sort of data storage for a typical survey?
Yeah, you're probably talking, maybe sort of 200 to 300 megabytes a minute.
Okay.
Just as a very rough guide. It will depend very much on the SLAM environment and what's being measured. More surfaces, more points being recorded. But yeah, as a general guide, 200 to 300 megabytes per minute. acquisition.
Okay, so that's for the handheld side. Rodney, for your system, I guess we're thinking LiDAR rather than we're thinking photogrammetry. So I guess the LiDAR base of your system, do you have a bit of a rule of thumb on data storage?
With the Regal, it's probably about 4-5 gigs per half hour. But with the Velodynes, it was a heck of a lot more because the Velodynes had the 16 and the 32 lasers, and they were just absolutely gigantic.
Yeah.
So I really noticed the difference when changing to the Regal, how even though the data was much, much sparser, but it was more accurate. So it ended up, you ended up, what you might have got out of the Velodyne after you denoised it ended up being similar to what you had just straight off from the Regal.
Yeah, so it's saving you time and saving you
Storage.
noise data, and storage. So we're a few gigabytes per half hour. That's still with data sizes these days. That sounds quite practical. Lennon, would you have a comment on that as well? I guess with the Pegasus 2 system, you've demonstrated there it's an integrated imaging and laser system. Do you have a data rate, you think, for storage?
Yeah, obviously depends a little bit on the number of cameras you have on and the scanner speed, but 4.5 gigabytes a kilometre is a rule of thumb.
Okay, per distance. That makes sense because the images on the system are sort of distance-based interval, aren't they?
That's right. So you sort of specify the chainage of which you want a capture made. So obviously the more photos you take, the more data.
Yeah, no, definitely, that makes sense. We'll jump forward to the next question, which is from Pete. Thanks for your question, Pete. Going to your presentation, Rodney. Hi, Rodney. Thick grass scrub. Will the UAV LiDAR system penetrate these? And if so, how well and accurate? So I think your videos, I was really impressed to see, and I felt that there was some good answers there. But do you want to explore that question?
Thick grass, if it's vertically upright grass, no problem because it will go down through it. The worst grass is the kikuya, that dense matting grass, because that can be 0.5 meter thick and the LiDAR just doesn't have a chance. There's no gaps in it. So that's horrid. The other toy was also very bad because it's exceedingly dense at its center. And if you fly over the toy, you just end up with little lumps because the system thinks that it's hard ground when it's actually just this dense mass of vegetation. But as I said in the presentation, it doesn't take much of a gap to get down to the ground. But by the same token, you don't know that you're getting ground. You could get through the top canopy, and if there's 0.5 meter of detritus lying on the ground, that's what will get the return. So you need to have an idea of what is on the ground to decide whether what you're getting is the ground or not. So yes, the answer is normal grass, not a problem. Very, very dense grass, yes, it is a problem.
I think that's been my experience also working with the two vegetations you brought up are probably the two pain in the necks for my work that I've worked through. The Kikuya, I think high altitude airborne LiDAR, we see that as a problem there as well. That we wish it never came to New Zealand. We've saved some surveyors. We'll jump ahead to the next question is from Caleb for UAV LiDAR. So a question for you again, Rodney. If there's no place for ground control, then would you need direct referencing with onboard GPS rather than a SLAM solution? I guess that's the question for you, being the UAV mounted system. Are you using a SLAM solution, Rodney, and what would you go for that question?
No, the systems I've got have both had GPSs on the drone, and that's what's used to geo-reference the data. And it has proved to be surprisingly accurate. considering the size of the GPS that's actually on the drone. The result of the processing of the trajectory in Inertial Explorer, it's saying that these trajectories are down below 3 mil for position and 5 mil for height in the trajectory after that processing. It's what it's saying is amazing, but because the lasers aren't that accurate, then you can never claim that your final data will be that accurate.
Yeah,
but the SLAM, yes, you can get systems that will be using the SLAM on the lidar, on the drone, and you've got to georeference it somehow. So you would then either have to have ground control, but with our system, because the georeferencing is directly on the drone and then through the trajectory, we don't need to have ground control. I usually have, even in places where I can't get any other control, I will have one where I launch and land from, just as a final check on the height adjustment, to make sure that that aspect of it is correct. But I found that the positions have always been very, very good.
No, it's some good feedback there. It brings to mind with the mobile technology and the handheld technology, you're prone to suffer GPS outages, but with the UAV system, I don't think you're flying under anything that's blocking your satellite, so why not have a GPS?
That's right. We've got, as soon as it's up 20 meters in the air, then you can put your occlusion angle down to 0 effectively. Yeah,
and you've got beautiful GPS coverage throughout the whole. So, but doing that check to check at your takeoff at minimum, to check your offsets, your lever arms and that, and check that your datum is genuinely matched, that definitely makes sense. We'll jump ahead to...
Sorry, Sam, what I also usually do, as I said, is try and fly the photogrammetry as well, because I've found that the photogrammetry processing has always been pretty good. And that gives me another independent surface that I can use to check against the LiDAR. And I found
so that'll be photogrammetric processing from the same flight. It's not two different flights.
No, we do two different flights. My system is not. I don't have an integrated camera on my LiDAR, so it's two completely separate flights. The only common thing between the two would be the ground control.
Yeah. Okay, so it's an independent survey to a degree.
Yeah.
Yeah. So a question from Felipe this is to Rodney, directed to Rodney. For large areas covered by dense vegetation, to extract under the Canopy data, do you use terrestrial data to calibrate your ALS generated model? So I guess that's exploring again the ground control idea, but do you use ground surfaces as a method of control?
Usually the places we're surveying, there is no ground surface. That's the reason for the survey. So I'm not quite sure I understand the question.
I think the question is directed that do you use terrestrial surveying as a way to control or calibrate the datum of the survey?
Oh, I see. No, I don't. Yeah, generally these places, to get in there to do the survey is so prohibitive. I mean, that's the reason we're flying them in the first place.
Yeah. Would you overextend, maybe if you're flying some new bush area around an existing quarry or mine site, would you overextend onto the existing mine site as a method of checking a match?
Yeah, there's often overlap from the system because the range, especially on the Regal, the range is so big that we'll get overlap out onto open areas, which we can use as a check.
Yeah.
But effectively, all that checking is the open area. You've still got to make the assumption that it's what you're getting in underneath the trees is working.
Is genuine ground, yeah. And I guess behind the scenes, there's ways to explore the point cloud to try to understand what are you getting and what if it's ground or not ground.
I've found that I get more differences in the process of going from the point cloud to the surface, where you have to decimate down to a particular triangle size for delivering onto another client or to go into another software, than in the cloud itself. There's a point cloud you could be getting 20, 30 points per square meter, or 400 per square meter with the HDL32. But you've got to knock that back to a triangle that's across a triangle model across the whole surface. So you've got to make reductions in data with that triangulation. And often that has more of an effect on accuracy than the initial point cloud.
Yep, that's technology hardware-wise. That's good to hear that the hardware is doing the optimum data collection and optimizing those workflows, or maybe the client's software could be more powerful and he can afford to take a higher quality product from you. That's all the questions we've got up on the board at the moment. Do any presenters have a question that they could raise with one of the others?
A question for Allan. With your flat planes, Allan, would it be possible to put something in the area to use to create some structure? I was thinking of a couple of wooden pallets, perhaps leaning against each other. Just spread them around.
Oh, absolutely, yeah. So that's a common practice. If part of your survey area is not rich in objects here, introduce some artificial targets, whether it's park a vehicle, machinery, or some pallets, whatever's available that's convenient.
Right.
That makes sense. Can imagine you bringing all your mates to park their cars down the road, and then you can sort out the survey with no problem.
If it's an open area, if the most of the survey's open, get the GPS or a robot out, right?
Yeah.
Yeah, use the right tool for the job.
Well, this is right. Yeah, because I found that by the time you've gone through the processing of the data, and then you decimate it down to reasonable size, you might as well just gone out and walked it in the first place.
Mm-hmm.
Exactly, yeah. So use the right tool for the job, that's the best advice.
Yeah, excellent. So we're at about just over an hour there. I think we need to call time. Thanks all the presenters for presenting today. It's a voluntary effort on all their behalves. So we really appreciate all your contribution, preparation, and input today. And thanks all the attendees. Cheers.
Thank you.
Thanks, Sam. Good job.